In this lab, we investigated hydrates, specifically how to identify an unknown hydrate by determining the amount of water in its structure. This experiment relates to AP chemistry topics such as stoichiometry and the determination of chemical formulas. The primary goal was to identify the unknown hydrate from a given list by analyzing the weight loss after heating, which would correspond to the water content. Our pre-lab hypothesis was that the identity of the hydrate could be determined by comparing the experimentally measured water to the theoretical amount calculated for each compound before the lab. During our experiment, we used equipment such as Bunsen burners, evaporating dishes. We made sure to follow all safety precautions, wearing goggles at all times during heating, and we monitored the hydrates to make sure that they wouldn't oxidize and to prevent any splattering from the evaporating dish. We also made sure to safely handle the heated materials, either using a glove or using tongs. Finally, we developed new lab skills, including the proper use of a Bunsen burner and identifying the endpoint of heating when a hydrate has released all its water. By carefully analyzing the data collected during heating, we were able to work toward identifying the unknown hydrate.
Hi, my name is Auther, and I'll be going over section 2, which is the experiment. So we started by measuring how much the hydrate weighed before and after heating, and we did this by finding the weight of the empty crucible and then subtracting it from the total weight. Heating the hydrate made the water evaporate, and then we used the weight change to figure out how much water was in it. With this data, we could calculate the percent water and figure out what our unknown hydrate was. So in our first trial, the hydrate weighed 1.22 grams, and then after heating, it lost 0.62 grams of water, which meant that the percent of water inside was 50.82. In trial 2, the hydrate weighed 0.99 grams, and after heating, it lost 0.41 grams of water, which meant that the percent of water was 41.41%. As for the trends and patterns, we saw that heating always made the hydrate lose water. The amount of water lost matched the percent of water in the hydrate. And in trial 1, it showed more water loss in trial 2, which could have meant that we didn't heat trial 2 as much as trial 1, or that the samples that we had were a little bit different. So as we heated the hydrate, there were a couple of things that we noticed. We noticed that the wet hydrate started to shrink and turn powdery. And then as we started to heat it more, some of the hydrate started to jump out of the crucible, which could have been one of the reasons that accounted towards our percent error. And then for our major results, the hydrate was about 41 to 50% water. And then heating it made the water go away, which made the weight go down. We chose this method because it was simple and easy, which also minimized the risk for mistakes. Heating the hydrate allowed us to see how much water was lost, and then by checking the weight before and after. And then it was just overall a super basic experiment and gave us good data to find out how much water was actually in the hydrate.
Okay, for this lab, we used substance B, and after heating up the substance twice, we got 0.62 grams of H2O, which over the original amount of the salt made it 50.82% H2O. And that's probably really off, mainly because apparently the substance oxidized while we were heating it, because apparently we picked the one that's oxidized easily. For trial 2, the original weight of the substance was 0.99 grams, and after heating, the substance became 0.41 grams. Well, no, the weight of the water was 0.41 grams. And then, so the weight of the water over the weight of the substance made it 41.41% H2O, and I'm pretty sure that's also a bad result because it probably oxidized again since we put it on high heat for like a kind of long time. Let's compare this to the results of another group who did substance B. You can see, well, they got somewhat similar results to us with a 0.63 grams of water for the first trial and 43% water, and 0.96 grams of water and 58% water. So I guess we either that's supposed to be the actual percentage of water, or both groups managed to oxidize it. And I think that's about it.
Here are the AP post-lab questions. For question number 1, we used the hydrate that we had from the lab, which was hydrate B, and we got AlCl3, and so we wrote AlCl3 plus H2O and used a double replacement reaction to write out AlOH3 plus HCl. And then once we got the total equation, we just balanced it each element out. As for question number 2, in order to calculate the mass percentage of water for the hydrate LiNO3 with 3H2O, in order to get the mass percentage of water, you have to divide the mass of H2O over the total mass of the total molecule. And so for H2O, since there are 3 moles of H2O, we multiplied the molecular mass of H2O, which is 18, by 3, which is 54, over 123. From this, we got 0.439024 and so on, and then we multiplied this by 100 to get the percentage of 43.90 percentage of water. As for question number 3, we know that in order to get the value of N, you have to divide the number of moles of H2O over the moles of the BaCl2 in this case. So first, in order to get the moles of H2O, we subtracted the sample of hydrated barium chloride, which was 5 grams, to the heating product, which was 4.26, and got a total of 0.74 grams of H2O, which was lost during this reaction. Then we took the grams and then turned that into moles, and then, and then in order to do this, we multiplied this by the number of moles of H2O over the grams of H2O, which was 1 mole over 18 grams, and got a total of 0.0411 moles of H2O. In order to get the moles of BaCl2, we took the remaining amount after the reaction, which was 4.26 grams, and then we multiplied this by the total number of moles of BaCl2 over the grams, which was 1 mole over 208.23 grams of BaCl2, and then we got 0.0205 moles of BaCl2. So with these numbers, we plug them back into the formula to get the value of N, which would give us 0.0411 moles of H2O over 0.0205 moles of BaCl2, giving us a molar ratio of 2. As for question number 4, we would have to get the molar ratio of H2O to COCl2. And to do this, we first got the grams of H2O by subtracting 1.98 grams from the original sample to 1.55 grams from the remaining sample to get 0.43 grams of H2O. We then converted this to moles by multiplying it by 1 mole over 18 grams of water, giving us 0.0239 moles of H2O. As for COCl2, we know that there is a final number of 1.55 grams, and in order to convert that to moles, we multiply that by 1 moles of Cl2 over 129.84 grams, giving us 0.0119 moles of Cl2. Finally, in order to get the original formula, we would get the molar ratio by dividing the total moles of H2O, which was 0.0239, over the total moles of COCl2, which is 0.0119. This gave us a ratio of 2 to 1, giving us the final formula of COCl2 by 2H2O. In order to ensure the complete removal of water from the hydration reaction, we can actually repeat this procedure just by reheating the sample and weighing it again. If the mass remains constant, then all of the water has actually been removed. As for question number 5, we will actually have to do another molar ratio between the moles of water lost and the moles of total salt. So first, we got the mass of the hydrate by subtracting the mass of the crucible and the hydrate minus the mass of just the crucible, giving us a total mass of 3.16 grams. Then from that, we got the mass of the salt by subtracting the mass of the crucible and the salt minus the mass with just the crucible, giving us just the gram of the salt that we used, giving us 1.361 grams of salt. Then I converted this to molarity by multiplying it by 1 mole over 95.211 grams, and then got us 0.0143 moles. Then, in order to get the mass of water lost, we actually subtract the grams from the mass of the hydrate and the mass of the salt, which is 3.16 minus 1.361, giving us 1.799 grams. Then I converted this to molarity, which would be multiplying this by 1 mole over 18 grams of H2O, giving us 0.0999 moles. Then, in order to get the mole of water, the ratio of the moles of water to salt, we divide by 0.099 moles of water lost over 0.0143 moles of salt, giving us a ratio of 7 to 1. And so the final formula would be MgCl2 by 7H2O.